Okay, we have just seen the simulated experiment including the capacitor and resistor. So here we will try to understand what we have seen using mathematical theory. Okay, so here we have a similar circuit with this battery and a resistor and a capacitor and also a switch. Okay, so what will happen if we turn the switch onto A, right? Then of course you can see that the complete loop is formed, so therefore the current will start to flow following the arrow shown here, and then let's call the current I. And first we will try to explain it qualitatively and then try to use some mathematics. Okay, so initially in the beginning the current will flow out from the battery and go through the resistor and then finally try to reach the capacitor. Okay, and then of course in the beginning there was nothing inside the capacitor, but as time goes on the charges will start to accumulate in the capacitor. As you can see, according to the direction of the EMF device, you can see that there will be positive charges here and negative charges here. Okay, and then when the charges are accumulated according to Q equals CV, the potential difference will appear across the capacitor. And then as you can see, when there are many charges inside the capacitor, the potential will also very big. And then when the potential difference in the capacitor reaches VEMF, which is supplied by this EMF device, then there will be zero potential difference across R. So in this case, according to Ohm's law, there will be also no current flowing through the resistor. That's when the current will stop flowing, right? Okay, so let's try to use the mathematical equations to explain what we have just said. Okay, so what kind of rule do we use in this case? Of course, let's try to use a loop rule because we have a complete loop. So starting from this position, let's go around the circuit clockwise. So first we come across this EMF device, so plus VEMF, and then the current I is going through this R, so therefore it has to be minus IR. And then let's call the voltage across this capacitor as V. And then here we have just seen that it will be plus charges on the upper side and negative charges on the lower side. So therefore, if you follow the direction of the current, the change in potential will of course be minus V, right? So that is why we have minus here. And then of course Q equals CV, so therefore V equals Q divided by C. Okay, and then we finally come back to the original position. So the total summation becomes 0. That is the loop rule. Okay. And then here what we have to realize is that in fact this current and the charge are not independent from each other, but they are related. How are they related? They are related by this equation. So current is the time derivative of the charge. So you can insert this into the equation and summarize it this way. Okay, so VEMF has moved to the right hand side. So here we have to realize that VEMF is in fact a constant. It does not change with time. And C is also constant, R is also constant. So here we have only one variable. You know, time is not a variable, but it's time is not independent variable. So time just flows, right? So we have only one variable we have to find out, which is Q. Okay, and in this case, this type of equation is called the differential equation because it includes the differential form of the variable. And we have seen something like this in the spring semester when we are dealing with oscillation with spring and mass. Okay, so and also you will probably learn how you can solve this type of this type of differential equation from Introduction to Mathematics or Calculus. So here we will not explain it in detail, but I will just show you the results. So the solution of this differential equation is given here. So please do me a favor. Just do it by yourself. Try to insert this Q into this equation and then make sure that this equation is satisfied. Okay, that's what you have to do. And trying to figure out this is really the solution. And then how does it look? It actually includes the exponential form. So if you remember the shape of the curves in the simulation we have just did, the shape is actually the shape of the curve comes from this exponential function. And then let's try to learn something about it. At t equals 0, which means in the beginning, how much charge does it have? If you insert t equals 0 here, exponential of 0 is 1, right? So therefore 1 minus 1 becomes 0. So therefore at t equals 0, q equals 0, which means there will be no charge inside the capacitor. How about very long time, after a very long time? So and then you have to insert t equals infinity. If you insert infinity, then exponential of minus infinity is just like 1 divided by exponential infinity, which is again like 1 divided by infinity, so it's like 0. So if this part becomes 0, then Q simply becomes CV. So therefore, after a very long time, Q is not 0, but is CVEMF. That is how much the charges can be stored in the capacitor. Okay. And then how about current? How can you get the current? You simply have to take the time derivative. And if you take the time derivative and if you know how to do the differentiation of the exponential function, then this will be what you get. Okay. And here, let's try again what happens at time equals 0 or infinity. If you insert t equals 0, then if exponential again of 0 is 1, so I becomes V divided by VEMF divided by R, which means that in the beginning, at the very moment the switch is turned on, current will flow by this amount. And then now this is actually an exponential of minus, so as a function of time, the current will decrease. And then when the time becomes very large, which is like infinity, then exponential of minus infinity will be like 0. So finally the current will become 0. So these two solutions satisfy the behavior as a function of time that we have seen. Okay, and you can also display the graph of the charge as a function of time here. So typically the the exponential function typically look like this, right? But exponential of minus t typically look like this, right? And then here we have 1 minus exponential of minus t, so that is why the graph look like this. And here we have 3 different curves showing different values of tau. Okay, I will explain this tau in the next slide. And if you understand next slide, you will also be able to understand this. Okay, please wait for that. Okay, and then suppose from the previous slide, you wait a long enough time so that the charges are fully accumulated in the capacitor, just like here. We have the positive signs implying that charges are accumulated. And then now suppose you change the switch from A to B. Then what will happen? Now, since we have formed another loop, the charges will come out and current will flow just like this. Okay, so here again we will explain it qualitatively first and then try to use the mathematics. Okay, so in the beginning charges will come out and then positive and negative charges will combine, so the current will be large in the beginning. But as when the charges are coming out, of course the amount of charge will decrease, so therefore eventually current will become 0. Okay, that's simply what's going to happen, and we call it discharging process. because the charges are coming out. So when the charge is coming in, it's called the charging process. When the charges are coming out, it is called the discharging process. Okay, during this time, okay, we already said that. So we will try to calculate using mathematical equation. And in fact, we have already used a loop rule in the previous slide. And then compared to the case of the previous slide, it's actually the same here, except that we have no EMF device, right? Previously, we had the EMF device and then the resistor and a capacitor, but here we simply have no EMF device. So in the previous slide, we had the VEMF on the right-hand side, but here we have nothing. So it's simply 0. Okay, so instead of explaining step by step, we have just used the same equation, same differential equation from the previous slide, but simply put the right side to be 0. This is the case which is applied to the current situation. Okay, and then again we have the differential equation, including the time derivative of the Q and also the Q itself. And of course, the solution must look similar because we have a very similar differential equation with small change on the right-hand side, which is a constant, right? So in this case, again, I'm showing you the solution. And here, actually, the solution of Q looks like this. And then here, try to, again, insert this guy into this equation and make sure this equation is satisfied. And here, one new thing is Q0. What this Q0 simply means is the initial charge. Which means that you can start this process with whatever charge you have, and then equation will simply look the same. So make sure that this Q0, size of the Q0 does not matter when you insert it into this equation, okay? And then, so again, let's try to see what happens as a function of time. If you insert t equals 0, then exponential part will become 1. So at t equals 0, Q is Q0. That is the initial amount of charge. And when the time passed long, very long, then let's insert t equals infinity, and exponential of minus infinity is of course 0. So at the end, Q becomes 0. So finally there will be nothing left, right? And how about current? In the beginning, the current, of course, you also insert t equals 0, and then this part becomes 1. So current, I is minus Q0 divided by RC, okay? And this minus symbol of the current actually means that now current is flowing opposite direction with respect to what we had in the previous slide, okay? And what if you insert t equals infinity? Then again, exponential of minus infinity is just like 0. So current also becomes 0 at infinity. So in the end, there will be no current flowing, right? Okay. And this equation, this graph shows you how the current changes the function of time. And then, so this is what the exponential of minus t kind of function look like. It will start from certain value and immediately decrease. And then here again, there are 3 colors shown here. Okay, so the red curve, which is shown with some tau value with 0.5 second, is decreasing rapidly in a short time, right? But in comparison, this blue curve with tau value 2 seconds, which is larger than 5 seconds, is also decreasing, but rather decreasing slowly. Or if they're very long time after, these become more or less similar, but in a short period of time, they behave a little bit differently, right? And this tau is actually is called a time constant, capacitive time constant. Okay, it's called a capacitive time constant, and tau is defined as RC, which is actually over here. Okay, so it's just like exponential minus t divided by tau, right? So let's think about it. Now, if tau is large, then in order to reach certain value, t also has to be large. If tau is small, then this function can reach the same value when t is small. So what it implies is that if tau is large, then it takes a long time for this function to decrease. So therefore, that is why with tau large, then it was going down very slowly. But if tau is small, then it goes down very quickly. So this value, which is RC, gives you an idea how quickly this current will decrease or current will change. Okay, so then can you guess why large value of tau or large value of RC will make the change very slow? Why the circuit or the current in the circuit will change slowly when you have a large R or large C? First, if you have a large R, the amount of current will of course small, right? According to the Ohm's law. So therefore, small flow of current means a small flow of charge. So therefore, it will take very long time to get rid of all the charges, right? And at the same time, what will happen if you have a large C? If you have a large C, it's just like you have a very large bucket. If you have a very large bucket, then of course there will be a large amount of charge. So then it will take a long time to get rid of them. So that is the reason why the time constant becomes larger when you have large RC. Okay. Alright, so these two processes, charging and discharging, is the very important properties you have to understand when you have the capacitors. Okay, and it will also be very important later when we are trying to learn alternating current, which is the current changing as a function of time. Okay. So finally, let's make a summary of this lecture. From this lecture, you have learned the electromotive force and the EMF devices. It was a new concept. Try to remember that electromotive force is not a force, but it's a kind of potential or electric potential. Okay. And then we also learned how to calculate the current using different methods like loop rule, junction rule, or potential method and everything, right? And then we also learned the Kirchhoff's rules, okay, which was just like, actually they are current, the junction rules and loop rules, right? Okay. And then we also learned how to calculate total resistance or equivalent resistance when there are many resistors connected to each other. And then we finally learned how the current changes with time in circuits when there are both resistors and capacitors together. Okay. And then in the next lecture, we will study these things. And actually, important thing is that from the next lecture, we will start studying magnetism. We will study magnets. Okay. So so far we have studied the electricity, positive charges, negative charges, and their flow. But from the next lecture, we will study North Pole, South Pole, like magnets. Okay, that's what we are going to learn. And eventually, we will study how these two, electricity and magnetism, are related to each other. Okay. So, thank you for your patience. This time, the lecture was a little bit, I hope it was not too boring, but it was a little bit difficult, right? So, please review it as many times as possible, and I will see you in the classroom. Okay?